A 50-story Ferris wheel so finely tuned that stopping would throw it off balance. Let's jump on and off the London Eye. You practically wear this jet ski. It's a radical rethink in watercraft design that lets beginners ride like pros. 4 times higher than Niagara Falls. A man-made lake, lots of power. Hoover Dam beyond the postcards. Red, green, and amber. The modern traffic light controls our movement. Let's look inside these machines and see how they work. This is the London Eye, the largest cantilevered Ferris wheel in the world. Ferris wheels are nothing new. They've been around since 1893. And none of them ever veered from the basic bicycle wheel design until the Eye came around. This big wheel is different. It's held up from one side, and while at work, it never stops moving. The Eye's designers had some complex challenges getting it off the ground, then getting it running. London's always been a big draw for tourists, but it's never been known for its skyscrapers. A bird's eye view here was always, well, for the birds. So, for the new millennium, London leaders held a design contest to create a top-of-the-world view. There were 3 conditions. Be reasonably priced, keep the footprint small, and make it easy to disassemble. That's because they planned to take it down in 5 years. But the Eye was so popular, they kept it as a permanent fixture of the London skyline. The first challenge was just getting the wheel to the building site. The River Thames has 2 problems: 6-meter tides and a lot of obstacles. Easy enough for small river traffic, but getting large bits of the wheel through narrow passages like the Thames flood barrier and numerous bridges meant perfect timing with changing water levels. The tightest squeeze they faced had a clearance of less than ½ a meter. Getting it here through an obstacle course was one challenge. But nothing like the second problem, getting it up. In construction terms, this site at Jubilee Gardens is a postage stamp. Not nearly enough land to assemble 1,700 tons of metal. All they had was the river. They placed the Eye's pieces on 8 temporary islands, where they were put together. Then, the wheel was pulled up to a 65-degree angle. After some adjustments, it was swung into its final position. These cable backstays anchor the Eye into 33 meters of concrete. So, it's up and it's secure. How does it keep smooth and stable while carrying up to 800 passengers at a time? For that, we need to look to the Eye's pods and some pretty special truck tires. 32 glass pods attached to the Eye's outer rim. Each holds 25 riders and weighs 10 tons. That's a lot of weight hanging off the edge of a wheel. And these pods don't swing back and forth like the seats on a typical Ferris wheel. The Eye's pods each have a built-in leveling system to stay horizontal. There are 2 bearing rings for each pod. The inner part of each ring is fixed to the wheel structure. The outer part is fixed to the pod. So as the wheel turns in one direction, the pods rotate the other way to maintain their horizon. Each pod turns on these circular mounting rings, while the leveling system keeps everything running smoothly. Each rotation takes 30 minutes. Each pod traveling just under 1 kilometer per hour, 6 times slower than a casual stroll. That lets passengers step on and off without the wheel ever having to stop. And it gives you a lot of time for these great views. This spindle at the eye's center holds the whole thing together. 23 meters in height, together with the hub, weighs over 300 tons. 64 spokes stabilize the machine, along with 16 rotation cables. These attach to the hub at an angle, preventing lag in the eye's rotation. The wheel itself is turned by this set of truck tires. Hydraulic motors turn the tires, and the rotation of the tires turn the wheel. If you're up the eye in bad weather, these dampers fixed around the rim prevent vibration caused by high winds. That could weaken and wobble the entire structure. Not quite the ride that sightseers line up for. They buy their tickets to get an unparalleled view of one of the world's great cities on a machine that delivers exactly that. An elevator, observation deck, and great ride all in one. Almost 50 stories high in a city shy of skyscrapers. The only view of London worth the ticket. There are 3 basic classes of jet ski. There's the familiar sit-down model. Big, solid, great for cruising. The sporty stand-up model, designed for extreme tricks, but not something you master on vacation. Then there's this guy. A prototype called the Samba. Inspired by race bikes, it's one of the fastest jet skis on water, with radical features that lets a beginner ride like a pro. Let's see how it works. To make a jet ski maneuver like this without trashing its driver, you gotta respect the laws of hydrodynamics. That's why the Samba is built super light, only 90 kilograms, so it gets up to speed in a heartbeat. This other beast weighs over 3 times more and has to push a lot more water out of the way getting up to speed. Add a top-of-the-line custom engine to the Samba, and you've got a machine with a crazy power-to-weight ratio advantage. To see what powers a jet ski, take a look at this rocket, demonstrating that every action has an equal and opposite reaction. And all jet skis are water rockets. Push a stream of water one way, the machine goes the other. Its powerful water jet is driven by an impeller, which is pretty much a propeller jammed into a tube. Impellers take water in through a wide opening and force it out through a smaller one. This creates what's called a Venturi effect, where low-pressure water behind the impeller pulls more water towards the blades, increasing its speed. And when moving, extra water is rammed into the housing through a scoop, maximizing the jet effect. At its top speed, the Samba spits out enough water to fill your bathtub in half a second. The impeller is powered directly by the engine. That's fueled with a custom mix of high-octane gasoline and nitrous. Every bit helps. But after several years and a few blown engines, Samba's designers discovered that speed wasn't just about engine power. It's about how the machine contacts water. So, they came up with a radical new hull shape for a smoother, lower friction ride, and allows them to easily hit speeds over 60 miles per hour. All right, it's skinny and fast, but a low-friction ultralight body and a powerful engine are one thing. Controlling them, another. The designers wanted much tighter handling than other machines. All jet skis turn the same way. The steering works by changing the direction of the water jet from side to side. But it's not enough to get you doing this, or this. Leaning on one of these won't do much. This machine outweighs the driver 4-to-1. But the Samba weighs about the same as its rider. So you change its angle of attack with a simple body lean. A light frame and low driver position perfectly positions the machine's center of gravity. The driver's race bike crouch looks cool and aerodynamic. But in terms of handling, it allows instant communication between body and machine. In this position, the driver's center of gravity is the area framed between his shoulders, hips, knees, and extended wrists. And this sweet spot gives you maximum control over the machine for tricks and turns. But even the perfect weight ratio and a low center of gravity won't make it easy to do spins like this. With its new hull, the Samba's been overcoming friction for maximum speed. Now, to spin some real tricks, it wants all that friction back. And it does it with these wings that stay out of the water until you lean into them. Then they catch. This creates so much friction, it turns the water into a fixed point around which the machine rotates. It's a bit like pitching a pole into the ground and spinning around it. A natural move for the next generation of jet skis. Just don't take it too far. Or on second thought, go ahead. You don't need to be a pro to rock this machine. A low-slung driver position, radical hull design with lots of speed and control. Which is why you may see a lot more of this machine on the water. If you see it at all. Water provides 1/5 of the world's electrical power. And it's done with some of the largest machines ever built. Hydroelectric dams. Let's check out a famous one, Nevada's Hoover Dam, and see how it works. A machine like this blocks a river to form a deep reservoir that creates water pressure to drive turbines that produce electricity. Sounds simple enough, but the challenges facing dam builders are enormous. First, how do you block a river that doesn't want to stop moving? With a lot of concrete. In the 1930s, it took 5 million barrels of cement and 2 years of pouring to build this retaining wall. Pressure from all that blocked river water is so immense, they built the wall's base over 2 football fields wide to hold it back. And it's not a single block of concrete either. Because as concrete dries or cures, it gives off heat. This much concrete poured in a single block would have produced so much heat that it would have taken over a century to set. So, the wall is actually a series of individual blocks that cooled one at a time after they were poured. They were locked together with notches, like pieces of Lego, and then glued with a thin cement mix. With a concrete wall over 4 times the height of Niagara Falls. Only one major feature makes it strong enough to hold back the Colorado River. The dam's shape. See how it's curved? It's built in the form of an arch, which spreads the force of the water evenly toward the solid canyon walls. No weak spots. There's enough water pressure in Lake Mead to literally impact the Earth's crust. The canyons behind the dam hadn't felt anything heavier than air for a long time. So as the reservoir filled up, its weight in water caused hundreds of small earthquakes. The first time, unsuspecting geologists understood that man-made reservoirs can impact the Earth's surface. The next challenge for the hydroelectric dam is to harness enough water pressure to produce electricity for 500,000 homes in California, Nevada, and Arizona. Not bad for a machine that doesn't spit out a single puff of smoke. What it does spit out is water pressure, the key to this machine's output. Sure, running water can create power, but not nearly as much as water under pressure. Think about washing dirt off your car. Which would you rather use? We thought so. And Hoover's turbines need the same thing. So, the dam takes water from its reservoir through 4 intake towers, down 9-meter-wide pipes to the machine's turbines, located almost 50 stories beneath Mead's surface. Water is pulled down by the force of gravity. As it descends, the water pressure increases. The deeper you go, the stronger the pressure. And down here, the pressure is bone-crushing. More than 100,000 kilograms per square meter. That's like compressing 2 elephants into a shoebox. The pressurized water flows from the intake tunnels into these tapered pipes. The tapering effect creates a water jet that blasts into Hoover's turbines. But to manage the machine's electrical output, the water has to be controlled. These wicket gates open and close to change the amount of water spinning the turbines. There's enough water rushing through here to fill 15 swimming pools in 1 second. Okay, the turbines are spinning. What now? How does all this add up to electricity? A shaft connects each turbine with a generator, which houses a whirling assembly of electromagnets spinning next to a ring of copper coils. The swirling magnetic field literally pushes the metal coil's electrons around, and that's what creates electrical current. Hoover's got 17 turbine generator combos that send all that electricity out to an array of transformers, which then send it out to the grid and to all its customers. When it was finished, it was the largest concrete project in the world. Tourists may flock here to marvel at its size and beauty. We come to see how simple it really is. Block water, pour it down a man-made hole, spin some turbines, make power. Nothing to it. Red, amber, and green. It's a language the whole world gets. There are subtle differences in signals from country to country, but their function is the same. The modern traffic light studies, predicts, and controls our movement. Large cities deal with millions of cars every day. Drivers may feel like they lose a lot of time waiting for lights to change, But traffic lights are meant to keep us organized as we move. Let's see how they work. The problem with city traffic is that it's never the same. At many big city intersections, you'll see a traffic control cabinet. It's a watchdog that keeps tabs on the traffic flow of its intersection. And it often gets the information it needs from here. Buried just beneath the pavement, a metal sensor keeps track of cars as they pass overhead and sends the data back to the control box that adds it all up. A program then adjusts the timing of the lights according to its car count. The control box information makes it back to here, a command center, where info comes in from all kinds of places. The pavement sensors, traffic cameras, 911 calls, road crews, traffic reporters, and of course, the police. All this input helps operators change the timing of traffic lights on the fly. When they're not doing that, they study simulators to help predict traffic flow at an intersection, and then reprogram the lights according to the results. These boxes also come with a program called a conflict manager. It makes sure that no one gets hurt from mixed signals. If anything falls out of sync, the box defaults the intersection to a single color. Speaking of color, let's see how the lights work. Halogen bulbs illuminate most traffic lights, but LEDs are taking over. They're brighter, which means safer. They last for years, which means low maintenance. And they save power, up to 80%. The light-emitting diodes in an LED lamp are laid out in patterns. They allow for faster switching and can even contain different color displays and patterns in a single lamp. In a growing number of cities, traffic light control systems also play a crucial role in getting emergency vehicles through traffic, with help from a remote device that changes lights on the fly. Don't we wish we all had one of these? It's a remote control light changer. It's called an Emergency Vehicle Preemption System, or EVP. And it changes traffic signals to clear intersections for emergency vehicles. Devices flash secret-coded infrared or light signals to a receiver that can detect an EVP from up to 900 meters away. Once the pulse has been received, the lights change as needed. This reduces response time for emergency vehicles and makes intersections a lot safer for other vehicles in the area. So, the next time you're waiting for a red light to change and you feel like you're just another number, relax. The box on the corner may just reward you with a string of green ones down the road.